Ever imagine a world where energy is almost unlimited? A world where electricity can be generated without carbon emissions, without long-lived radioactive waste, and using fuel that exists almost everywhere. For decades, scientists have pursued one of the most ambitious goals in modern physics, recreating the power of the sun here on Earth. This technology is called nuclear fusion, and if it works, it could transform how humanity produces energy forever. But achieving fusion has proven far more difficult than anyone expected. Today, governments and private companies around the world are racing to solve one of the greatest engineering challenges in history. The question is simple. Are we finally close to unlocking fusion energy, or is it still decades away?
Did you know that modern civilization runs on energy? Every second, billions of devices around the world consume electricity. Factories operate continuously. Data centers process enormous amounts of information. Transportation networks move people and goods across the planet. But the majority of this energy still comes from fossil fuels. Coal, oil, and natural gas remain the dominant sources of global electricity production. These fuels are powerful and reliable, but they also produce carbon emissions that contribute to climate change. Renewable energy sources such as solar and wind have grown rapidly over the past 2 decades. However, they depend heavily on weather conditions and require large storage systems to provide consistent power. Nuclear fission offers another solution. It produces large amounts of energy without carbon emissions. Yet, fission reactors generate radioactive waste and carry significant safety concerns. Because of these limitations, scientists have been searching for a fundamentally different approach, an energy source that is powerful, clean, and sustainable. That source may be nuclear fusion.
To understand fusion, we must look at the stars. Inside the core of the sun, enormous pressure and temperature force hydrogen atoms to collide and combine. This process is called nuclear fusion. When 2 light atomic nuclei fuse together, they form a heavier nucleus and release an extraordinary amount of energy. This reaction powers every star in the universe. The challenge is that fusion requires extreme conditions. Temperatures must exceed 100 million degrees Celsius. That is hotter than the center of the sun. At these temperatures, matter becomes plasma, a highly energetic state where electrons separate from atomic nuclei. Containing this plasma, without destroying the reactor itself, is one of the greatest engineering problems scientists have ever attempted to solve.
Recreating fusion on Earth requires machines capable of handling extreme conditions. One of the most widely used reactor designs is called a tokamak. A tokamak is a large, donut-shaped device designed to contain plasma using powerful magnetic fields. Inside the reactor, hydrogen isotopes such as deuterium and tritium are heated to extremely high temperatures until they become plasma. At this point, the fuel becomes a swirling, superheated gas of charged particles. But plasma cannot touch the walls of the reactor. If it did, the reactor structure would melt instantly. To prevent this, scientists use powerful magnetic fields to keep the plasma suspended in the center of the chamber. This technique is known as magnetic confinement. The plasma forms a glowing ring inside the tokamak. If scientists can maintain the correct temperature and pressure long enough, fusion reactions begin to occur. When fusion happens, energy is released in the form of high-energy neutrons and heat. In a future fusion power plant, that heat could be used to produce steam and generate electricity, much like in traditional power plants. However, controlling plasma is extremely complex. Even small instabilities can cause the plasma to lose confinement and shut down the reaction. That is why fusion reactors require incredibly advanced engineering.
Although the concept of fusion is simple in theory, achieving it in practice is extraordinarily difficult. There are 3 main challenges. The first is temperature. Fusion requires temperatures above 100 million degrees Celsius. The second challenge is plasma stability. The plasma inside the reactor must remain stable long enough for fusion reactions to occur. But plasma is chaotic and constantly tries to escape confinement. The third challenge is energy balance. A fusion reactor must produce more energy than the energy required to run the system. For decades, this goal remained out of reach. Fusion experiments often consume more energy than they produced. However, recent scientific breakthroughs have changed the situation. In 2022, scientists at the National Ignition Facility in the United States achieved a major milestone. For the first time, a fusion experiment produced more energy from a reaction than the energy delivered to the fuel. This event is known as fusion ignition. Although this experiment does not yet represent a commercial power plant, it demonstrates that controlled fusion is scientifically possible. Fusion research is no longer limited to a few laboratories. Today, it has become a global scientific race. One of the most ambitious projects in the world is ITER, currently being built in southern France. ITER is an international collaboration involving more than 30 countries. Its goal is to demonstrate that fusion reactors can produce far more energy than they consume. The machine is enormous. Once completed, ITER will be the largest fusion reactor ever constructed. At the same time, China is developing its own advanced fusion experiments. The East reactor, sometimes called the artificial sun, has already achieved record-breaking plasma confinement times. Meanwhile, private companies are entering the field with innovative reactor designs. Several startups have attracted billions of dollars in investment, hoping to accelerate the development of commercial fusion power. The competition is not only scientific, it is also economic and geopolitical. The country that masters fusion energy could reshape the global energy landscape. If fusion energy becomes commercially viable, its impact could be revolutionary. Fusion fuel is incredibly abundant. One of the main fuels, deuterium, can be extracted directly from seawater. In theory, a single glass of seawater contains enough fusion fuel to produce enormous amounts of energy. Fusion also produces no carbon emissions during operation. Unlike fossil fuels, it would not contribute to climate change. Fusion reactors would also produce far less long-lived radioactive waste compared to traditional nuclear fission. Because of these advantages, fusion could become a major component of a future clean energy system. Cities could be powered by compact fusion plants. Energy shortages could become far less common, and the global energy economy could become far more stable. However, scientists remain cautious. Although progress is accelerating, building reliable commercial fusion power plants will require many more technological breakthroughs. For more than half a century, nuclear fusion has been described as the energy source of the future. And for many years, that future seemed permanently out of reach. But the situation today is different. Advances in materials science, artificial intelligence, and supercomputing are helping scientists understand plasma behavior in ways that were impossible just decades ago. New experimental reactors are achieving temperatures and confinement times that once seemed unattainable. Private investment is accelerating innovation, and international collaboration is bringing together some of the brightest scientific minds on the planet. Fusion power may still take years or even decades to become widely available. Yet every new breakthrough brings humanity closer to harnessing the same force that powers the stars. If scientists succeed, fusion energy could transform civilization, providing clean, abundant power for generations to come.